Good afternoon, all. I, Sarlati, Assistant Professor, Department of Electronics and Communication Engineering, Sri Venkateshwara College of Engineering, Bengaluru, Karnataka. Welcome back to second technical session. In morning session, we had a resource person, Mr. Sridhar Artham sir, gave session on compressive sensing and multimedia signal processing for 5G. Sir delivered the concepts of compressive sensing, multimedia processing, DSP and optimization techniques in 5G, case study related to QDSP and ARM architecture. Today's second technical session on compressive sensing techniques for next generation wireless communications by Dr. Jijesh J J, Associate Professor, Department of Electronics and Communication Engineering, SVCE, Bengaluru. On behalf of management, principal, and head of the Department of Electronics and Communication Engineering, we welcome you, sir, for this event.
Thank you.
Now, I'd like to introduce the resource person to the participants with the brief profile. Dr. Jijesh J J is currently working as Assistant Professor in Electronics and Communication Engineering Department at SVCE, Bengaluru. Sir received the BTech degree in Electronics and Communication Engineering from Kunur University in 2006 and earned MTech degree in Electronics from VTU University, Belgaum in 2010 and awarded doctorate degree in the field of wireless communication from Vishweshwaraya Technological University, Belgaum in 2019 under the guidance of Dr. Shivshankar sir. The area of the interest includes wireless communication, sensor networks, embedded systems, and communications. Several research proposals have submitted under these streams to various prestigious bodies like AICTE, DST, VGST, IEEE, and KSC-ST, and have received funds. He has been actively involved as a coordinate member in various committees such as AICTE, NBA, VTU, NAC, coordinator of Internal Quality Assurance Cell, etc. Sir has more than 37 publications in his credit in various prestigious journals. He has been IEEE EICT International Conference Coordinator since 2016 and has served as jury reviewer for IEEE Conference, IET Journal, and IEEE Journal. Guided more than 20 students in BE and 4 students in MTech, research scholars at university level. He has given many technical talks at various industries in the past and institutions in past. Now I'd like to request Dr. Jijesh sir to start the second session on compressive sensing techniques for next generation wireless communications.
Yeah, thank you, madam. Just I'll go for the PPT.
Thank you.
Yeah, just let me know then.
Yeah.
Yeah, it's visible.
Yeah. Yes, sir.
Okay.
Yeah,
So
you can start.
good afternoon to everyone. First of all, I will be thankful to AICT for providing us a wonderful opportunity in this STTP and funding for the department. And I am very much thankful to the management, principal, Dr. Shivashankar sir, head of the department, and my guide, and all the ENC team for the successful conduction of this event throughout. So we have this as the second slot, and I'm thankful to my parents, my dear ones, and all the participants and the entire ENC team for supporting to organize this event. So first of all, I would like to inform you that we are going to have the slot 2 in this. We have compressive sensing techniques for 5G cellular networks using MATLAB. It comes under AICT STTP program. So in this occasion, I would like to give a description about the compressive sensing techniques for next generation wireless communication. Here we'll be discussing on the compressive sensing techniques for various wireless communication aspects. And here I'll be discussing with you the compressive sensing. What do you mean by compressive sensing, and how it can be useful for a research scholar or a whoever does good research and contributes to the society. So this is what basically we will be discussing on. Myself, Dr. Jijesh, Associate Professor and IQSC Coordinator, Department of ENCE and Sri Venkateswara College of Engineering, Bangalore. So here I will focus on the outline of the presentation. First of all, we'll have an overview of the compressive sensing, what compressive sensing is all about, and what we are going to understand here is the entire scenario where compressive sensing fits in for the research, and what is the use of taking up the topic of compressive sensing. So that is what my overview will be. Then we'll be going and we'll be discussing on the next slide. We'll be having wireless communication based on compressive sensing, how the compressive sensing is going to impact on wireless communication aspects of technology. Further, we'll be having classifications of compressive sensing. So in classifications of compressive sensing, we'll be seeing what are the different places the compressive sensing acts, and where it can give some impact in the technical aspects of that. Then the most important one is the algorithms in compressive sensing. What are the major algorithms present in compressive sensing, and how these algorithms can help you in enhancing the research for further. All those things we'll be discussing in that. Looking up further, we'll have some research initiatives in compressive sensing. As a research scholar or a PG student or a researcher, it's very important for us to know what initiatives it has on the in the research. And I would like to make it clear for you that this compressive sensing topic is having a great boom in the upcoming research, and when we search in even in internet also, we find very less number of documents with respect to this. So it has a lot of research aspect in this field. And further I'll be discussing on the security aspects of compressive sensing, and followed by the compressive sensing deployment using MATLAB. So I will explain that how this compressive sensing can be run in a MATLAB, and how this code works and all those things. I will be just going in brief, not too much in detail. With respect to MATLAB, I'll be discussing that in the upcoming slides. See this, I wanted to include this as one of the slide for that is online availability, and which is very important. Most of us really don't know that where these documents, like some codes are also available in online, and it's very difficult for us to find out where it is there. So I will be just briefing you those things where these things are available. If you are really interested to go with this topic, you can have these websites, and you can go deep into that, where so much of material is available. Further, what is the potential research in this field, and what are the research issues when you do some research in this domain? So compressive sensing, we'll be discussing the research issues and potential research of that. Further, as usual, we'll have some applications of compressive sensing, and then followed by future contributions, like what contributions you as a researcher can contribute to this compressive sensing field, and how it can impact the entire research domain. So that we'll be discussing with that, then concluding the section further, and so first of all, I'll start with the compressive sensing overview. So in compressive sensing overview, I want to make clear that where this compressive sensing fit in, first of all. So that is what I'll be discussing with you. So what where the compressive sensing fits in, actually, if you take the entire communication system, we have a lot many 5G applications available, then so many industry applications available. So that will be the entire huge picture of that. Inside that, further, if you go further, narrowing down, see, when you are doing a research, no, the narrow down process is very important, and you have to focus on a small portion of the research so that you can contribute better in that domain. So that's the reason I have come out with this. Then you have the sensor networks, then satellite communication process, and the wide area networks and all. So these all things comes under the communication part of it. But I don't want to say that. I want to say, like, compressive sensing can be focused in so many technical aspects, like it can be used in optical communication. It can be used in so many places where the image comes into picture. It can image processing application. So everywhere this machine learning concepts, wherever you are using, there also you can use this concept of compressive sensing. So it is having a domain in this field, and you have cooperative communications and in network processing and all those things. So that is where the compressive sensing really plays a role in the field of research. So coming further, you have a if you consider that you have an image with you, and see, nowadays the data, we talk about 5G technology and all those things, where the low latency and high rate of data transfer, everything takes place. So can you imagine that how much of data will get generated over a decade of time? So it will be a huge amount of data which is going to be deposited in various parts, and it will be very much difficult for us to get retrieve it back. So if you are like, you can see, if your mobile or laptop have lot of data, what you will be, either you have to flush it out or you have to compress the data. So same process is taking place here also. You will be using this technology to compress the data, and when you compress the data, no, you can have a better process of communication aspect, or we can offer some security to that. All those things comes into picture. So this, if you take an image, you know that it's a combination of so many pixels, and you also know that it's a combination of zeros and ones and all. So further, when you take a image, you have to do the process of data compression. So this process of data compression I'll be discussing in detail further. So I am just saying you an overview of it, what the compressive sensing main role is. So when you have a data compression process, then it has to be stored in the data has to be stored, and then with the help of transmission, you transmit the information, and it has to be received. Then again, you retrieve the data, you have to decompose it, and then you can use it for your requirements. So here, this is the entire overview of the compressive sensing. So in this regard, I just will take you through the definition of compressive sensing, and what compressive sensing or compressed sensing. So in most of the domains, some of the researchers use compressed sensing. Some of them give it as compressive sensing, compressive sampling, or space sampling. It's all the same. Only thing is that what you can see here is the signal processing technique for efficient acquiring and reconstruction of signal, by which comes under linear systems and all. So this is what it is going to take place. The principle that it has the optimization process, which see, all the technologies, it adds some value when you go with the optimization process. And the compressive sensing also has the same process. You have to go with the optimization process to get a better process of research in that domain. So here also, the sparsity of the signal can be exploited to recover it from far few samples, and you use the Shannon-Nyquist sampling theorem, which you are very much familiar with it. And here they call it as new Shannon-Nyquist, because they add on some further research in that, and they make sure that the sampling process is done in a very systematic way, so that you get retrieve the signal much better compared to whatever you have in the current technology. So that is what, see, if you are sending a signal and you compress it, it's not that important. But when you retrieve it at the receiver end, you have to make sure that whatever signal you have sent at the transmitter should be the same which is received, and there should not be much of the loss. See, loss will be there, and some of the losses will be there, but try to see that it is not visible, or it is not going to create any impact further. So that is what you have to look into when you are stick on to the compressive sensing techniques. So that is what here we can see that spare is one of the sparsity or spare. This is one of the term which is commonly used in compressive sensing. See, if you consider a M cross N matrix, so what you can understand there, if there will be M cross N elements in that, what you have to understand here is, if you call it as a spare, means you will have more number of zeros available, and all the things will be concentrated to the diagonal part of it, diagonal part of the matrix. So what you can see is, when you are retrieving it, no, you have to retrieve the entire image. So that is the reason why you keep all the zeros is you have to reduce the size, and all those part comes into picture. And for calling it as a spare, you have to make sure that 50% and plus elements should be zero. If you have 3 cross 3 matrix, means at least you should make sure that 5 to 6 elements should be zero, and you have to make sure that the image doesn't fluctuate from the original aspect of that. So that is called as optimization process as well, where you should not disturb the image or any signal. It can be a signal or an image, whatever information you pass it from the sender, so that information should not get disturbed. So you have to make sure that it is maintained by doing all this process of optimization, or using any algorithms, whatever you design. You have to make sure that it doesn't change its properties. That is the maximum that what you can do. Beyond that, if you do it, the signal or the image will change its property, and you will not be receiving the same. So that should not be there. So our thing is that how best we can transmit it with all these technologies available, we have to check it out. So that is the role of a researcher. So two things which is required to retrieve the conditions are recovery conditions are, first one is the sparsity, which requires the signal to be sparse in some domain. So that is the first one, and second one is incoherence, which is applied through the isometric property of sparse signal. So these are the two conditions which you say that when you retrieve the signal back from the receiver end. So some of the requirements of compressive sensing: we have high density of sensor and high speed sampling. You have a large amount of sample data will be discarded. That is what it will be happening is, most of the some of the part of the images will be considered, and rest of the images will be discarded. So but still it has to retrieve you the same image what you have sent from the sender. So that is one thing, and minimum number of samples is required in order to perfectly capture the band limited signals. So some minimum number is mandatory to have, which can give you a decent output at the output end. And spare signals has high dimension and can be perfectly reconstructed from measurements with low dimension by solving the optimization process. So see, that is what wherever we talk about, if you're going with the spare signal also, you have to keep in consideration the optimization process, wherein you can see that the optimization process plays a major role, because if you are not uh, considering the optimization process, what will happen is you will not receive a proper image at the output, or you will not make use of the process to the maximum extent. Like, if you are not setting the correct optimization process, or you are not making maximum usage of optimization, what it will happen is you will not be going too much deep into the research. So that is very much required. And what are the benefits of compressive sensing is, so some of the benefits, like when you really go into it, you can see that random projections can be possible, and encryption of the signal, and robustness to noise. So that is very very important when you think the compressive sensing part, that robustness to noise. So it will not get too much affected with noise, and you have to make sure that, because you have made most of the part to be zero, and you are just concentrating on the diagonal part of the matrix. So what it will happen is the subjection to noise will also get minimized, and scalability is a very great benefit of compressive sensing, and low complexity at sensors. So these are called as some of the benefits of compressive sensing, and which can be used in order to focus upon the research aspects of any of the in this field. So just to, I want to take you through little bit of mathematics, not too much, because when I just browse through the compressive sensing or reconstruction of the entire scenario, you can see in most of the papers they have given a detailed description of this measurement metrics and transform metrics and reconstruction process and all those things. But if you are really interested, you can just go through that mathematical part of it, where they deal with the matrices, and they generate the reconstruction metrics by multiplication process and all those things. So here you can see that compression and reconstruction process will be discussed here. The block representation of the compressive sensing is being shown here, where you can see you are having a signal X, and the process of compressive sampling techniques is to be carried out at the initial stage. So what we'll be doing is the sampling process, and you can make sure that you do the compressive sensing sampling, and wherein you generate the matrix phi. And once you generate the matrix phi, it is called as a measurement matrix, and further the signal will be converted to Y. So the X will be converted to Y, and so once the process is done, then you have to go with the quantization process. As all of you are great researchers of so much of domain, you are very much familiar with all these things, the process of sampling, quantization, and all those things. Then the signal will be transmitted further from the transmitter. Once the signal is transmitted, you have to make sure that the process of noise and all those things should not get into it, and you have to security aspect as well, you have to check in. Once the process of quantization and the transmission is carried out, the signal will be received at the receiver end, and at that time you will go for inverse quantization process, and your process is now to retrieve the signal back. So you have sent the signal Y from the transmitter, and you will be getting Y dash. Why you're getting Y dash? Because why not Y? Why it will be Y dash is some of the signal might have lost, or some of the signals might get added to it as the part of noise, or the process can have a slight deviation from what you have transmitted. Then it's not enough for us to retrieve the signal Y. It's required for us to get back the signal X. So for that process, we have to go with the optimization process. So this complete block is called as the compressive sensing reconstruction. So we have to reconstruct the signal back. So we have quite a lot of algorithms for that, for the reconstruction process. We will be discussing those things in the later stages. So when you have compressive sensing reconstruction process, you have to go with optimization and inverse transform function. So we usually take an example here. It is given as IDCT cosine transform. We go with that, and we have to go with the optimization process. Then the signal will be converted as S. You can see in the figure, and when you completely complete the reconstruction process by using, you can use so many algorithms are available. So those algorithms we'll be discussing further. This is just, it will give you a block diagram representation of how the construction, compression and reconstruction is carried out. Once it is done, you'll be finally ending up with a signal X dash. Why again X dash? Because you have been given a high resolution signal at the input called as X. You might not have received the entire signal X as it is. You might have received some losses, and because of that, the signal will get converted as X dash. Then you have a X dash can be written as psi into S, and psi is called as a transform basis. So all this very brief, I have given you the mathematical part of it. So you can see that dimensions are mentioned here, m cross n, m cross 1, n cross, yeah, 1, all these things. You have a matrix representation for that, and sparsity also will come into scenario, and wherein you have all the elements, more majority of the elements, like we say that more than 50% of the elements of a matrix has to be zero. So that is what it has to be done here. Further, you look into the aspect of x dash, you can see that the image whichever you receive will be whatever you receive will be having some noise. So you can do some process to eliminate those things, and finally you can use it for your requirement. So that is what, by using this compressive sensing, what are the major things what you can understand here is, you can have a better signal transmission. You can avoid the noise interference to it, and also you can look into that the transmission of the signal will be faster. So these are some of the things, and you have this phi is equal to psi into psi. That is the equation which basically deals with compression and reconstruction process. So this is what you can see the illustration of the entire scenario, whatever I was discussing to you still now. You have a matrix, X, where you have the information being transmitted. So first what you are going to do, you are going to do the process of compression, wherein the random projection process is taking place. And once you see, your X has been converted to Y. So further, this Y has to be transmitted using any antenna setup, or the entire transmission block diagram for that it is there. You are very much familiar with that. So those things we'll be using it in order to transmit the signal to the receiver, from the transmitter towards the receiver end. So this signal, whatever it is transmitted at this point, you can see here, and which is received at the receiver end. Further, you have see at the process of transmission, so many contents might get added, so all those things has to be retrieved. So recovery process has to be done. There you have L1 norm minimization process, and which helps in recovery of the signal in much faster way, and which gives a better performance compared to rest of the algorithms whatever it is there. Still research is going on in so many domains of recovery, where the researcher can recover a signal much faster and much accurate by avoiding the noise content in this, and you can try to extract the information how much percent, like whether you are able to get it the entire image as it is with the high resolution, is it possible. So all those things plays a major role in this compressive sensing techniques. So this is what the entire scenario of compressive sensing works out. So if you are really doing a research, I would suggest you that you can go with the recovery part of the compressive sensing, where you can design some algorithms which can outperform the existing algorithms and come out with a better results. So this is what you can see here. It's quite interesting, and I wanted to just show you a live example, whatever it is there in compressive sensing. So if the transmitted signal is X, and you do the encryption process, and you receive a signal Y, then you have the channel transmission. Through channel you will be having some EV, is nothing but some noise being added to the communication system. You have a key of A, and which helps to protect the information from being lost by, or being means the security aspects come into picture. So that is what then you retrieve the information, and further you get back the original signal whatever it is transmitted. So this is again represented in a very systematic way, where you call it as a crypto system, where here you have step 1, step 2, step 3, step 4, and step 5. So here you can see that you will be sending the information at the center part, and then you'll be using CS algorithm, compressive sensing algorithm. It is not mandatory that you have to use this algorithm. You can use any algorithm whichever you prefer, which can give you a better output in the later stages. You have also options to mix the signals. You can take two images and like you can mix the images, and further if you mix the images it becomes pretty more difficult for anyone, so more security aspect will come into picture, and becomes very much difficult for anyone to retrieve the original image whatever you are sending, or the original data what you had sent to the receiver end. So here you can see that one of the example I have shown you, that is 32 frames has they have taken 32 frames, and by the process of compression what has happened is it has been compressed to two compressed frames. So you can see the image is so blurred, and it you cannot make out what actually it is. But when you retrieve the image back, you reconstruct the frames, and you make sure that you get the original image back, and you can understand what really happened there. So it's the courtesy of the authors, and we have a live example which we can see that how the entire scenario works. Further, moving on to the compressive sensing, what contributes to the wireless communication. So here we'll be discussing on the wireless aspects of channel. With respect to channel, you have compressive sensing based and you have scarce based distributed compressive sensing, MIMO process. Then you have circulant matrix, multi-carrier system, and cooperative network. So these are some of the wireless wiretap channel process which can be. It's a survey conducted on compressive sensing on wireless communication systems. So these are the things which you can look into. Then you have further, if you move on, you have Internet of Things, where the compressive sensing can be brought into consideration, and where you have adaptive compressive sensing for smart objects, frequency selection, and static environment. You have Internet of Multimedia of Things, as the author has means in the morning presentation you have seen that there are many multimedia process being discussed, and those things comes under this aspects. And then you have security with respect to cloud environment and all those things. Some other wireless communication scenarios like crowd sensing, smart grid. We are doing some of the research in smart grid, and we have been sponsored some event, some fund for that in by the for by DST and some other organizations. By that, some research is going on in the department, and we have wireless body area networks, and that is the area where me and my guide we had a great deal of research in wireless body area networks. But see, we have not used compressive sensing. I have gone through this compressive sensing at the time of research, but we have not focused on compressive sensing in wireless body area network. Why? Because the reason behind why we have not selected is in our research is like when we take medical information, no, when you use the compressive sensing part of it, you might, like if you take a ECG signal and all, if you may lose some information, means it's going to create a lot of impact further. So that is the reason we have not touched upon the compressive part of it. But if you are using some places where like if you are going with temperature or some other data where it's not going to have a significant impact on the medical domain, you can go with the compressive sensing. There is no problem. But if critical things and all, it's always preferable that you have to be very careful. Each small information is going to have a lot of impact in the medical domain. So that is what we have checked into, but for our research we have not gone too much depth of compressive sensing. Further, we have wireless sensor networks where the secure measurement matrices are there. Then protected compressive sensing, captured medical data gathering, and compressed detection. So all these things comes under wireless sensor networks. Further, you move on to the security aspect of compressive sensing. Here, see, compressive sensing with respect to security has a great impact to research. And if you are really focusing on compressive sensing, you can focus on the aspect of security as well, where you will be going with the Gaussian measurement metrics and circular measurement metrics, then random matrices, then so many specifying basic part of the measurement metrics, random uh, process, and random matrices as part of measurement matrix. So these all things can be considered with respect to the security aspect. When I went through some of the research articles, I have seen that Gaussian measurement matrix has been taken more compared to rest of the things. And you can look into, as per your application, it can vary. It's not mandatory that you have to go with this kind of thing for your research. So based on your requirement, it will vary from one end to another. So these are some of the wireless communication based on compressive sensing. This is very important for us to understand the compressive sensing techniques. So compressive sensing can be classified into two, that is sampling metrics techniques and reconstruction techniques. In sampling metrics technique, you have it's a wide range of things are there in sampling metrics, like fast Fourier transform, discrete cosine transform, random metrics. You will come across some of the things in the curriculum, but so many things are there which you can look into and exploit it further. Then circulant metrics, random demodulation metrics, and random convolution metrics. So these all things comes under the sampling metrics techniques. Then you have the reconstruction techniques. See, I am focusing it again. Reconstruction is a very important plays a very important part in compressive sensing techniques. And reconstruction techniques has quite a lot of algorithms. It's not yet come into the existence in much detailed manner, but I can say that in next 5 years it will be a huge demand to get a compressive sensing technical aspect of compressive sensing into the real time scenario, because every company will look into, or every organization will look into a researcher who can really contribute to compressive sensing. Because I have told you that in next decade, because of the 5G coming into existence, the entire scenario of data has to change. And because you will be uploading, see, 1 or 2 months. So because of this COVID situation, we are sitting at home, and I can make sure that at least 50 to hundreds of videos has come from whoever is participating as of now itself. So can you imagine that how what is the scenario of the entire globe? So that is going to happen if this continues further. And you will be you have to go with the process of compressive sensing techniques to in order to have a better means you can have a better process of research, and you can have a better output. So this compressive sensing, when you go with the reconstruction techniques, it is classified as convex relaxation iterative algorithm and greedy algorithm. In the first one, we have L1 norm minimization techniques and gradient descent. It varies based on your requirement. These are the most important algorithms which we use for the reconstruction process. In the greedy algorithm, we have matching pursuit and orthogonal matching pursuit, compressive sampling matching pursuit, and generalized orthogonal matching pursuit, and so on. Many are there. I have just listed a few, and these are the I have told you that greedy algorithm is what I have seen in most of the scenarios, in most of the research contributions. But it depends on the way you take it, and it has some plus points and it has some negative points as well. So you come out with, if you are really going for a PhD or for a doctorate degree, you can come out with a new algorithm which can contribute to compressive sensing. And if your performance outperforms compared to the existing algorithm, it gives a great contribution for the research, and you can make it sure that this is will be a great technology in the upcoming days. So that is what for doing that you can I will come in much detail in the next slide. So compressive sensing matrices are also playing a major role. You have Fourier transform, or where here I'll be discussing some of the matrices, its concept and strength and weakness. being a research scholar or a researcher, it's very important that which metrics to select, which algorithm to select, what is the advantage of selecting that algorithm, what is the key points of selecting that matrices, whether this algorithm in the future is going to help you in enhancing your research. All these things is very much important for everyone to understand. So for that, first our guide also suggests us, when you are going for a research, please go with the literature whatever is existing and understand in depth what real contributions has been carried out in the domain. So I'm very much thankful to Shivshankar sir for guiding us in right direction and uh, being with us in all the areas of research. And I have learned a lot from sir, and it's still the process of learning. So there, if I go with the matrices being selected, we have quite number of matrices, and see your strength and weakness is also available. So in your research, if the strength has more contribution to do than weakness, you can go with that matrix. That is how. But the entire this kind of a entire cumulative research has to be done, research has to be done. You have to keep on searching for new concepts, and you have to understand that whether it is going to contribute for you or not. So here, going with the matrices, I'll discuss on Fourier transform, where the concept is randomly selected rows and distributed discrete DFT process, and its strength is easy to implement and fast recovery. So if your research needs an easy implementation and fast recovery process, you can go with that. But it has some weakness also, not universal. High uncertainty is there, not accurate. So can you hide the weakness of the metrics in your research and focus on the strength and come out with a good impact in the research aspect? So then next one is random metrics, random projections, recovery with high efficiency, easy to implement, universal. You have weakness like M knowledge required and more memory required. So if you are, its memory is a major concern in your research, you cannot go with random metrics. Then circular metrics, the entries are independently distributed in one row, and randomness is reduced is one of the strength, and fast recovery is also one of the strength. It's not universal, is one of the weakness for that. Then random demodulation metrics. See, why I have brought this slide for you is understanding all these metrics is very important when you are going with this thing. And you may be using like deterministic metrics for your research because it is fast, or you may be using DCT, design discrete cosine transform, because it is simple and easy to implement. So based on your concept, based on your involvement in the research, see, please keep a note of this matrices. If you are really going with compressive sensing, this document is going to help you a lot. So then you have Gaussian and Bernoulli matrices, which is independent and identically distributed, and simple and easy to implement, is one of the strength and universal. Its weakness is costly. See, in the morning presentation also, sir has mentioned that the cost of hardware is high. So that is what, if your technology cannot withstand high cost on hardware, you cannot go with Gaussian matrices and all. So those things you have to look in as per your as per your requirement. You have to deviate your research, and as per the requirement of you, or as per the requirement of the society, or as per the requirement of the company or industry, whatever is looking into this domain, you have to deviate your research in that aspect, and you have to come out and you have to satisfy the requirements whatever it is therefore in that domain. Then only you call it as a research. Okay. So the satisfaction of yours and satisfaction of see, first satisfaction of yours is important, and once you are satisfied, you can make the research in a very high boom. So deterministic matrix is another which has a fast and reduced memory usage is its strength, requires high number of measurements. Then we have random convolution matrix, and which has simple and easy, and it is universal. It has some weakness, like can only recover noiseless signals and more number of so if there is some process of noise and all, we have to look into whether we can use it or not. Then this DCT, which has simple and easy to implement, more M required and missing data recovery. So all these things are called as the compressive sensing matrices, which can be looked into when you really go for a coding process, and when you want to retrieve the signal back from the original signal, means after the process of compression. So we have been discussing quite a lot in the last previous slot. We had 6 days of slot, and we have been discussing the key aspects of 5G and 5G technology, what 5G is going to contribute, and all those things. See, I would like to focus in this aspect that 5G has a great impact in the society, and means great impact with respect to the technology, and this compressive sensing in collaboration with, see, 5G is a huge technology, and compressive sensing compared to 5G can play a minimal role in 5G technology. So compressive sensing is going to impact 5th generation by trying to security aspect, or going to focus on so many parameters, and by the compression of data and all those things. So compressive sensing has some models. We can call these are the some of the models. That standard compressive sensing model, one of the thing which is existing now, standard one, which you can rely upon and you can start your research. Then you have signal separation by space representation, block space signals, and mmv, called as multiple vector measurement. So these are some of the four compressive sensing models. If you are going with respect to this research, you can really focus on these things. Key technical directions in 5G is, you know that 5G has low latency and high speed of data transfer, and all those things which in the previous lecture also we have seen. So key technical directions, what this can contribute to is increased spectral efficiency and large transmission bandwidth. It can contribute to large transmission bandwidth in 5G, and better spectrum reuse also is some of the key technical directions which compressive sensing can contribute to 5G technology. Yeah, this is the most important part of thing when we go with the research scholars or PG students, or whoever is interested in research. That is the algorithm part of any of the technology. So compressive sensing algorithms are widely applied in wireless communication. Some of the algorithms I have classified, like convex relaxation algorithm and greedy iterative algorithm. Then you have orthogonal matching pursuit algorithm, then iterative thresholding algorithm. See, I am not going to go deep about all these things, but what you can see is, if you at least know these algorithms, no, you can check whether its performance is better. For that, what you have to go with is, you have to understand what are the algorithms existing in compressive sensing. Then you have to read some research articles based on these algorithms, and you have to see that whether greedy iterative algorithm is outperforming L1 minimization algorithm, whether it is doing that or not. If it is doing so, in what all aspects it is doing, whether it is going with respect to noise or security, or which aspect it is going to provide a better performance. That is what you have to see, whether it is reducing the size of the thing or all those things. So they would have done a detailed study in the literature, or they would have done a detailed study in the research section. So you have to understand that, and can your developed algorithm perform better than these algorithms. That is what the research is all about. So L1 minimization algorithm, iterative soft thresholding algorithm is one of them, and iterative reweighted least square algorithm. These are some of the L1 minimization algorithm. See, most of the research articles which I have been going through, I have seen that greedy algorithm and L1 minimization algorithm is what they have used frequently, because of their so much of plus points and less negative points. So that is what you can also see. If you are interested in these kind of algorithms, please go in depth of these algorithms and understand these algorithms performance in all the matrices, and is it feasible for your research work or not. So those things you have to do a detailed study with respect to compressive sensing algorithms. And these all algorithms can be used at the retriever part of it, and where you retrieve the signal back to the normal state. So then you have combination and sublinear algorithms and non-convex minimization algorithms and Bayes inference algorithms. So these are some of the key algorithms which you can look into, which has really helped in performing and retrieving the signal back to the original state. So these are some of the algorithms which were used in wireless communication, and it's not mandatory that you have to go with these same algorithms in wireless communication. You can have still further lot many algorithms may be there. You can do a detailed study on those as well. These algorithms can be also used in some of the communication, like optical communication, or some of the places as well. You can merge these algorithms and you can modify as per the requirement, image processing, all those machine learning concepts. Also you can see to that whether when you incorporate this, you have to merge the technologies and check whether the technology can contribute better, whether the system can contribute better. Like when you merge like some concepts of machine learning into it, and you check whether it is having any impact, whether it does anything better compared to the existing one. So all these things comes under this compressive sensing algorithms. And further, just I thought of comparing two algorithms to give a brief description about which stands better or in which places. So like I have just classified two algorithms I have taken for your understanding. You have convex relaxation algorithm and greedy algorithm. So if I am doing a research in this compressive sensing, I will go with in detail of convex relaxation algorithm as well as greedy algorithm, and I will try to understand that whether the convex relaxation algorithm has performance in which all domains, and which matrices it has a better understanding and performance which it can contribute to the research. As well as the same way I will go with the greedy algorithm as well, and I'll try to look into that where the greedy algorithm contributes better, and what are the strength of greedy algorithm, why greedy algorithm performs better in some of the aspects in convex relaxation algorithms. All those study will be carried out first initial stage. Further, I will come out with a see. I will not be starting my research from zero. It's not preferable to start any research from zero. It will take years together to come out for a successful output. So what you have to do is, it's always preferable that you start your research from the existing research, like whatever it's already existing, you look into that and you try to modify and check whether your contribution can lead at least 10 or 20% extra than the existing algorithms and whatever it is there in this field. So if I go with this too, I will be doing a detailed study. So just to make you clear with how it has to be done when you are doing a research, that's the reason I have just put two algorithms as a comparison. So you can see that both the algorithms can be tested for recovering space solution given sufficient measurement. Both does better. And next one is guarantees stable recovery. Both of the algorithm does very good, so there is no need to bother about those things. But rest of the aspects, when you come with the algorithm, convex relaxation algorithm requires few measurements. This requires more measurements for perfect reconstruction. Can you contribute that? Whether are you ready to have more measurements for a perfect reconstruction? That is what you have to look into. Then convex relaxation algorithm is complex, and the other one is simple and easy to implement. Then this one is more accurate, this is not accurate. Whether you really need accuracy in your see, if I am going with the healthcare related applications, no, I need accuracy. I cannot sacrifice accuracy. So I have to go with convex relaxation algorithm. So I cannot go with greedy because it doesn't give me accuracy itself. And accuracy is most important in healthcare domain. So that is what you have to look into. Then high processing time and low processing time. So these are the some of the key comparisons of convex relaxation algorithm with greedy algorithm. And if you are really interested, you can merge some of the things, and you can research on that, and you can come out with a new algorithm which has the good impact of greedy algorithm and some good impact of convex relaxation algorithm. That is what the research really needs from your end. Okay, so which can give a better output when you finally do the entire research scenario, means when you simulate the entire process. No, that is what you have to check in. So it's very important for me to say that what are the initiatives of compressive sensing in the field of research. Here you can see that, as I was talking about ECG, EEG, and EMG, and all those things. So this these things will be collected with the help of a sensor. See, if you are going with some medical related applications, no, you go for a very high, so high sensors, high which can give you precise readings, and without any fluctuations, or no, not even the noise should not get added into it. So when I was also doing the research, I had to go with high sophisticated equipments where it was being imported, and we have done that part of the research. Then here, this process of, then after accumulating the data from the sensors, no, you have to go with compressive sampling. See, I have told you that compressive sampling I will not prefer for medical data such as ECG and all those things, but like other information like pulse, or go with temperature and all, compressive sensing can be can be looked into. So we have a compressive sensing process, and here the training data set database can be seen, where the data pre-processing process, all this will be carried out, and sensing metrics training process is also done in this. Then further it is merged with the compressive sampling. And why we are taking help of training process and all those things with respect to this is, see here, for me accuracy is important. For me, the data should not get lost. It should be as it is when I receive at the receiver end. So this is that online learning process also can be looked into, and which will be compared with the space approximation process. And the entire if you are going with the healthcare related scenario, it's better you have to go with the comparison process, where you get a clear picture of whether any information is lost, or whether you have retrieved back the entire information. So in this, after compressive sampling, you take the signal reconstruction process. In the further, I will be going with the MATLAB, where I'll be discussing on two codes, where you can see that how it performs, and what is its output. So if I go with a plain image, as this is the another contribution by another author. So if I go with a plain image, I have to go with stage 1 and stage 2, where in stage 2 we have a space process of it. As I have told you that majority of the data will be converted to zeros, and we focus on the rest of the information. And then you have permutation process, and then compressive sensing. Here in compressive sensing, you can see the blocks getting merged to, that is SRM and 2D LASM. So what is SRM is random matrix, structurally random matrix, and two-dimensional logistic adjacent sign map. So these things can contribute to the compressive sensing. Further, you have the qualification process, and you get the secret message, secret information, or secret image. So that secret image, further, what this author has contributed is, this secret image further has been merged with the carrier image. So when you do the merging of the carrier image and the secret image, what will happen further, it becomes very difficult for you to understand that which image has been transmitted. So nobody can so it plays a great security aspect in this. And when you transmit the image, no one can recover the original image. That is the key of it. Then secret blocks into carrier blocks will be fit in. Further, the modify pixel values and rotate the blocks, and then the encrypt index, and further you get the chipper image. You call it as a chipper image, and continuation of that, how to retrieve it back. So this is what you can see in the next slide. So the reconstruction of the image for so it, you can see that stage 1 and stage 2, the down portion of it, your chipper image has been received at the extract of information, and you have to decrypt the index, and when you do that you have to restore the pixel values. So this is very important for us to understand that you have to restore the pixel values, and you have to do the entire process of restoring the image back. Then you have the extract secret image blocks. You have to remove the image from that, whatever you have added to it, and you have to further send the secret image. Once you send the secret image, it has to do the process of inverse quantification, and then CS reconstruction process. This is where the CS reconstruction process is where the algorithms will play a major role, where you have to see to that you retrieve the entire information back without missing out much of the data, and see the accuracy and precision. All this plays a major role in the algorithm performance. So those things you have to consider, and then you retrieve the back, and inverse pairs you have to do, and you retrieve the original image. But when you compare the original image with the reconstructed image, you can see a very minute variation, and that we call it as an error. We call that function as error, and how much error you can minimize it, that better your algorithm is performing. That is what you can understand from this. Further, it has a lot of applications on IoT platform, where you have a physical data being collected by various sensors and all these layers, and then this has to be further processed. So the processing takes place with the help of compressive sensing techniques, and you look into various algorithms for that. Then you pass on this information through the internet, and then you retrieve it. You have data fusion, data analysis, and data storage, encryption, and all those processes which takes place there, and you retrieve the information back at the application layer. When you retrieve the information back at the application layer, you can see that it can be used for healthcare, energy measurement, smart cities, and agriculture. So it has a very great impact even in the IoT platform as well, with respect to compressive sensing. When you talk about compressive sensing, so this is what compressive sensing, based on acquisition of the information. The compressive sensing collects all the information. It can be a heartbeat, temperature, or whatever information is required, whether it is industrial related, web camera related, or web cam information is collected, or whatever it is. The compressive sensed based acquisition techniques are used in order to do that, and then you go with the edge computing platform, where you have embedded platform, industrial PCs, and mobile computing. These are called as the CS based reconstruction process. Then further you go with the cloud, and then you retrieve the information in the application layer for like event detection, or crowd sensing, traffic monitoring, and all this recovery processing being carried out in the field of IoT as well. So IoT also has a great deal to do with compressive sensing. I will say that it has major contribution in IoT platform. Then when you talk about the three promising technical directions in 5G, so we have quite lot of things we have studied in the previous slot one as well on 5G. So I'm not going to too much stress you on 5G with respect to this. I just want to say that here in 5G as well, you can use these compressive sensing techniques, which can really contribute to improve the uh, transmission bandwidth, or spectrum use, or spectrum efficiency of the entire scenario. So here's spectrum efficiency. We have massive multi antenna techniques, and non-orthogonal multiple access. Then you have spectrum reuse with interface cancellation, and traffic load prediction, connecting massive devices, all those things. We have seen that we have gone with 2G, 3G, 4G, and 5G technologies, but 5G demands compressive sensing. 5G needs compressive sensing because of the major thing is that more number of data is going to be uploaded or downloaded, and it is going to contribute a great impact further. So transmission bandwidth also, it will like cognitive radio, ultra wideband, wave communication. I think further in future they will be touching with all these concepts of 5G contributing to cognitive radio, ultra wide band, and wave communication with respect to compressive sensing. So this is what you can see here. See in this image, it is very clear that you can see that space interfacing is taking place. You're going to have a path loss and high or low, and that color indicates where the path loss is low and path loss is high. Then you have massive salient users and common space component, individual space component. All these things, space interfacing is a major contribution to the 5G technology, where the real compression of the entire thing has to be going to take place. Then you know that you have to make use of the time domain as well. Like in daytime you will have more traffic, and in the night time you will have less traffic. So how this technology can impact in these fields also is a good research which can be contributed further. So low rank property of large scale traffic also plays a major role in the this massive process. So this is what you can see about 5G technology. See, without touching machine learning, it is very difficult to talk about compressive sensing. So we have nowadays, you can see that in most of the entire scenario, we club the machine learning concepts, and we try to understand that whether the machine learning has anything to do with the technology. So here also in compression process or compressive sensing or compressed sampling, you can see that the entire signal is retrieved, and the process of variation of data compression is being carried out. Then you have two processes. One is called as a training samples and testing samples. Then the compressed data has to pass on through the training samples and the testing samples. Why we do it, this training and testing is, next time when the same set of data is being transmitted, it becomes easy for us to execute and get a better performance output. So that is what this is what training sampling and testing sampling is done, where you have deep features of learning layer process. Here you have Gaussian input layer, hidden layer, pooling layer, and hidden layers are there. Then further the information is being transmitted, where the weight smoothing is done, and this process is then trained, and then you retrieve at the end here, where you merge the training and testing signals, and you understand that what are the future learning and false detections. So what machine learning can contribute is it can minimize the error part of it, and it can give you a better performance in comparison with the normal process. So it when you see that, you can look into more in depth with respect to these aspects. So security aspect of compressive sensing, I just will go with the security aspects of compressive sensing. Mainly deals with the Gaussian measurement metrics or circular measurement metrics and random matrices. Then you have some of the random permutation as part of the measurement metrics and multiple. So these are all security aspects of compressive sensing, where if your research is diverting towards the security part of it, these matrices can play a major role. Then application scenario, you have wireless sensor networks, internet of things, crowd sensing, smart grid, and wireless body area network. So if you talk about wireless sensor networks, establishing a secure measurement metrics is very important challenge what has to be done. And then you have capture medical data or whatever information is being sensed by the sensors. Then data gathering and compressed detection, all these things comes under the application scenario. And then you have adapt internet of things, means you have to go with the smart objects, frequency selection with the static environment, compressive sensing for multimedia things, secure interaction with cloud, and all those things. Then you have crowd sensing, smart grid, and wireless body area network. These are some of the applications. So this is the same. We have the wireless communication based on compressive sensing. We have the applications of wireless sensor networks. Internet of Things has a great deal to do with compressive sensing, crowd sensing, wireless body area networks, and smart grid, wireless wiretaps channel. So compressive sensing deployment using MATLAB. This is what I really want to focus upon. Two codes I want to execute for you, if time permits. That is open customable algorithm. That anything whatever you go with the compressive sensing, no, you have to write the entire code either using any of the. If you're going with MATLAB, then you have to write that process, how the channel, I mean how the compression process the uh, has been carried out, which algorithm, the functions of all that algorithm, you have to use that in a systematic way. And when you have to execute it and check whether the process of compression is being carried out. Then you have C++ and C, that you can make that file into a .lib and .dll or .exe file, and wherever it is required, no, you can run those things, and you can store it in the library, and you can do the further functioning of those algorithms. So this is what I will just check it out. One of you can just help me out whether it is visible. I'll just go back to the MATLAB, and I want to know that whether it is visible to you. So I'm just directly going to the editor window just to avoid the time lapse. Is it visible to you, madam?
Yes, sir, it is visible.
Okay, fine. Thank you. So here, this is what you can see, that one of the PhD student of the university has contributed this MATLAB code for compressive sensing as one of the example, wherein the frequency domain has been considered. It's an example of a signal in is pairs in frequency domain, and random signals are taken in the time domain aspect. So as usual, you have to set the path and all those things, and then going further, you have to set length of the signal, then number of random observations to be taken, and discrete frequency. I'm not going to go too much into depth. I want to give you an overview that these are the things what can be done in the compressive sensing, which can take you to further research. It's a very basic one which you can do it, and if you are really interested in that, you can look into for a further extension of your process. So you define the number of random observations, then discrete for frequency of two sinusoidals, that is k1 and k2 is defined, and spare signal frequency is what you have to set. So you have to define this sign of this function and sign of this function, you'll get x. And then further the plot and subplot and all those things, you are using x of f, fft of x need to be done. So this is what one of the research scholar has done in with respect to the compressive sensing environment. Then creating a dft matrix, and then going further, you will be going with the dft of the signal, selecting random rows of the DFT matrix, that is Q. You will be going with the function RAND then you have creating the entire matrix A. A will get created, and then taking the random time measurements. So this calculating the initial things and running the recovery algorithm. So this is the algorithm function which they have used to recover that. See here, they have used L1 EQ underscore PD. It is L1 equalization algorithm which I have discussed before. So based on that, or some of the algorithms you have already there, you can use it, and some of them you will be developing. You have to come out with and you have to compare it and do this. This is just plotting and subplot and label x label y label. Just I'll run the code for you. So this is what you can see here. Now this is the original signal with amplitude and samples. Then in the frequency domain, the signal will be obtained in this form. So this is just, I want to give an overview of it. This is one of the research carried out by one of the research scholar, and you can do your contributions. I'll go with the next code, which is this one. That is, you can see that same student has done in the example of signal in space in time domain and random samples. So here the same thing, he has set the path for that, and number of period samples per period, and then RF frequency is also set. Then the pulse repetition frequency is done, then sampling frequency. So you will be thinking that how to get this kind of codes in online. Those things also I'll be touching upon, where you can have this kind of things, and you can start your research in this domain if you're really interested in. See, if you're spending at least 2 years or 3 years of time specifically on a single domain, it becomes easy for you to contribute something. So it even if you are doing a PhD or anything, all these things need some dedication of yours and a regressive search in the internet. Okay, so that is what pulse frequency is also set, and sampling frequency. Once you set all these parameters, then you have to go with the uh, then generating the pulse train and all those things you can see here, taking discrete Fourier transform of the signal. Then all these things has been done, then creating a DFT matrix, then creating a measurement matrix, then calculating the initial guesses and running the recovery algorithm. So I see, being in this, we cannot take you through the live thing. If this is what you can just execute the codes in your hardware and try to see that whether MATLAB gives you a performance. See, don't innovate anything as at this point of time. Just understand whatever it is there in the compressive sensing, and innovation can be done once you understand the entire thing in detail. Okay, so let me run this code as well. You can see, so this is the original signal which has been and this is in the discrete Fourier transform process. So you get the signal in this form. So this is some of the things which you can go in much detail. I am just coming out of it. So I'll, is the slide visible, madam? Is the slide visible?
Yes, sir, yes, sir.
Okay. Okay, fine. This is what you have. It's visible, right? Yeah. This is what you can see in the example of frequency domain, and where you can understand that these signals can be done as per your requirement. Means as per this is a very simple approach which I have just taken you through that. But what really, if you are really contributing to the compressive sensing part of the technology, I preferably say that please go through this things whichever I am displaying as of now. That is that you can see that math work contributes a lot for almost all the technologies whichever it is there. And with respect to an example of compressive sensing, which is this data are available online, and I request you to just take this code and execute in the MATLAB, and have a check of it whether it performs or it gives the L1 minimization process, and how the spares vector works. All those things you can understand in much detailed way. So here in this the compressive sensing example, what really they talk about is they have a very good illustration of L1 minimization, and it also identifies the space vector, and x1 is also space vector, and a is the matrix which is given for you, and the coefficients can be checked out as per your requirement. This example can be used in order to check whether how this compressive sensing techniques work in the real time scenario. So you can just take down that link, and you can go to that and just download this code and execute and check whether you can have some understanding of compressive sensing as an example. So this is I just wanted to take you through some 3 to 4 websites where really the compressive sensing concepts has been explained to you in depth, and this is one of them. I am very much impressed with some of the websites where they have given deep compressive sensing, where you can see that the concept of deep compressive sensing is been executed. And here the here you can see that, here you can see, you can see the pointer, that code is there. No, you can, if you click on that code, you can download the entire code with respect to this research. That is theoretically guaranteed optimization framework for robust compressive sensing techniques. So if you are understanding, if you first, what you have to do is, it's a 2019 paper. So if you want, if you are really looking for a research, come out with a base paper. And it is always preferable that a base paper with everything, like base paper with code and everything which is available. No, if you take it, it gives a great impact for your research. And you have one of the author whom you can contact as well if you come into some problems in the future. So that is what you can look into. You have this paper, for example, if I take this is on compressive sensing, robust compressive sensing in of MRI is being done. If you click on the code, you will get the entire code, and you have to run it in the MATLAB environment and check whether it performs as per the author has discussed. So before that, you have to download the paper and check it out whether the paper results, and this how the author has done. What, see, you are all experts in MATLAB, and you can understand the code. And that also I will tell you, if one of the code line is not is you are not able to understand, please copy that and put it in the search line, and you can get a detail. Or you go in MathWorks and check it out, and you get the entire explanation for that. You don't have to depend upon anyone for understanding these things. That is what I really want to. It's all the dedication what you put in the field of research to get something out of it. So the next paper also talks about the deep neural networks. If you are really interested, you can download the code for that. See, I have just taken a snapshot of the window. There are many papers in the same thing you can have of your interest. Some papers might be relevant to your research, and it will really help you to enhance your research in a very higher pace, and it will take your research to a very good uh, progress. Okay, that is what you can do. So this things I just wanted to say you that these are the places where it is really available, these things. And further, I want to just go with another site as well, that is codeprojects.com, where they have discussed on machine learning gradient. See, if you are interested, you can ask your students to download this. You can ask your students to download this code and ask them to run it in MATLAB, come out with some results. It can be considered as a BE project, and you do some further modifications and understand much in detail. You can do many things in that. So this is how you can take up your research and go further. PhD means you can put in lot many things. You can understand everything in much detail. And here in this, we can see that convolutional neural network based image classifier and all those things is what you can understand from this entire page. You please go through that, where you they have gone through the compressed sensing introduction is also given, and how it can be merged with the MATLAB concepts. Further looking into the this website, I was so impressed to see that, where it is basically from comsoc.org, where they have very recent papers like 2017, 2019, and 2000, sometimes 2020 papers are also available. For the transaction papers are there. So what they have seen here, what I observed here is sharing is caring is what they have also mentioned. So that is all with which we have to talk about. Sharing is caring. We have to share as much as you can. And here also they have shared the simulation code, and somebody sharing a simulation code is a great piece of work. And I should acknowledge all the authors for their dedicated work, and they have shared all the simulation codes. When I have downloaded some of the codes are in MATLAB, and some of the codes are with the help of Python, because you have used the machine learning concepts and all those things in some of the papers. So they have gone with a deep complex of new networks, and they have gone with compressive sensing. So this is, you can see, signal detection, classification, and compression. This page, lot many things are there. Not only on compression, there are many other simulation codes available which you can try to download it, and you can run it and check. You see, when you're going with a paper, first thing what you have to do is, once you download the code, don't go for executing the code. First, to understand what the author has discussed upon, what is his impact on that paper, what he really wants to speak to you regarding that, and then you execute the codes. Try to understand the algorithms available in it, and to go much everything in detail it is given. Please note down this thing. It will be really helpful at this point of time, or in future it will be really helpful for you to understand where the simulation codes are available. See, research, you can talk about, if I talk about research, you can say that it is just collecting the information, putting it in the right place, and executing it, understanding it, and evaluating the performance of it, do some contributions to that. These are all contributes to the research. So potential research and research issues in compressive sensing. So potential research in compressive sensing is its performance limitations under the practical conditions, and general platform for compressive sensing, spectrum sensing, effect of antenna deployment, and measurement of channel also plays a potential research in this field, and channel estimation and joint support, channel estimation with feedback, unknown support. So see, this is how you should look into what are the potential contributions in this compressive sensing. And one more thing, the effect of antenna. See, if you are contributing to the antenna area, antenna configuration on the performance of compressive sensing enables the channel estimation is still an open research question, and it is not yet solved in any of the articles yet. If you are you don't go with a very high difficult problem, try to solve a simple problem and then go for the complicated ones. So these are some of the potential research in compressive sensing. And some of the research issues when you talk about the compressive sensing is how to construct the measurement matrix phi incoherent with the transform basis psi distributed. And how, second one is how to choose the transformation basis psi sparsity incoherent with the measurement matrix phi, or irregular sensor deployment, how this graph wavelength or diffusion wavelength. So all these things is what some of the research issues which the researchers are facing in the compressive sensing scenario. And you can take up of when you also work in compressive sensing, you will also have this kind of challenges which you have to solve it by the massive reading, and you have to understand the concepts in much depth. Okay. So coming further, we have the applications of compressive sensing, where the some of the applications of compressive sensing is linear regression and model selection, spectrum sensing, spared error correction, group testing, and data stream algorithms, compressive medical imaging, analog to information conversion, through the wall radar imaging, uh, single pixel camera, compressive processing of main field model data. So these are some of the places where the compressive sensing really looks into further. We have compressive sensor networks, which is in communication domain, compressive sensing aided localization, and compressive sensing based on cloud radio access networks. It can also contribute to impulse noise cancellation and sparse channel estimation, positioning, multiple access, and cognitive radio. So if you are really interested in any of the application, you can choose any of the application and you can work on that. So these are some of the things which really contributes to some future contributions, which can be as a technical contributions which you can look into is non-ideal channel propagation. You have the use of other compressive sensing based recognition algorithms. You can contribute some other algorithms which can as I was saying, before, which can really contribute, which can be a very good contribution for this domain. And stopping rule of iterative algorithms, then design of the sensing metrics. So these are some of the future contributions which nobody has done yet. If you see, if any one of the problem, if you take now, you can do it as a PhD research in any of the universities. So this is very open. I have discussed with you. Each topic can be considered as one of the challenge, and you can take it up. So in compressive sensing, to conclude with, before that to conclude with, we can see that compressive sensing provides a sub-Nyquist sampling approach to efficiently tackle the challenges for 5G techniques, and it has a theoretical research on compressive sensing based on next generation communication technologies has made substantial progress, but it's applicable for practical systems and can be further investigated. Then compressive sensing algorithms is very important, exhibits reduced complexity and increased reliability, as well as with current system and hardware platforms. And it is a promising potential feature directions. And the main challenge is to determine a suitable sampling metrics and how to address the complexity of in the hardware implementation process when you go with the implementation of the hardware. And overall, to discuss upon the compressive sensing, the research opportunities and technical advancement scenarios plays a major role in compressive sensing. And I stress upon that, to conclude with this, do a proper search on compressive sensing and come out with some algorithms in your research, and which can contribute to something for the society, and which can contribute to the research to have a better performance in so many matrices and all those things in the compressive sensing domain. And one more thing I want to focus upon is compressive sensing is the most recent uh, technology which is going to be there for another 10 years of time, and all the research contribution to this technology is will be a great contribution to this entire globe. So along with that, I thank Dr. Shivashankar sir for providing me an opportunity. I'm very much thankful to you, sir, guiding me throughout my research. And whatever I have delivered today, it's all your contributions given to me. And I'm thankful to my parents for being supportive, and my all loved ones. And I'm very much thankful to my ENC team for being so supportive in all the aspects of my research, and as well as any point of time they stand along with me. I'm thankful to AICT, and I'm thankful to the management, principal, and all for giving me an opportunity to talk in front of you. And always, I'm very much thankful to the patient listeners of mine throughout 1.5 hour time. I'm so thankful to you all, faculty members and students of various institutes. So my final thing is that please go deep into the research and contribute something. Share your documents, and love to learn. Thank you.
Thank you,
If you
sir.
have any queries, you can please discuss.
Participants, if you have any queries, you can ask in the chat box only. Any queries? Thank you, sir, for providing the knowledge on wireless communication based on compressive sensing and algorithm in compressive sensing, research initiative in compressive sensing, and security aspects of compressive sensing, examples on compressive sensing deployments using MATLAB, and also you have shown by using the MATLAB also, and sharing so many research related website details. I hope this will be very much useful for the participants and research scholars.
Yeah, thank you, madam.
And Any queries? No, sir. Still, no one has asked any queries. They're telling that very informative session and excellent session. Yeah, it was helpful for them. Only those feedbacks they have given. Thank you
Yeah.
very much, sir.
Thank you, madam. At least they can make use of all the information and they can
Yes,
progress in their research. Thank you.
yes, sir. And tomorrow we have session 3 and 4 by our resource persons. In morning session by Dr. Dilip Reddy Bolla, Associate Professor, Department of ENCE, SVCE, on the topic Compressive Sensing in 5G, Open Research Opportunities. And in afternoon session by Professor Rajendra Prasad, Assistant Professor, Department of ENCE, SVCE, on the topic 5G development with MATLAB. These are very informative sessions. Don't miss it. And I request all the participants to subscribe to our YouTube channel, STTP ECE SVCE, and also click on the bell button to get the notifications of each and every session. We would like to conclude day one of the AICT sponsored short term training program on compressive sensing techniques for 5G cellular networks using MATLAB. Thank you, everyone. Stay home, stay safe.
Thank you.